Lesson 7.6, we'll put our work with exponents together now and use functions to graph and to solve equations. Okay, remember that when we consider exponents and powers, 2 to the x power means that we are taking 2 and multiplying it repeatedly. Like 2 to the third means 2 times 2 times 2. Okay, so exponents show repeated multiplication. Okay, if we have 2 times x, okay, that is showing, okay, like 2 times 3, if x is 3. That means 2 plus 2 plus 2. Okay. It means 3 groups of 2. Okay. So multiplication, we remember from grade school, as repeated addition. Okay, back when you learned how to multiply first, you would say 2 groups of 3 or 3 groups of 2. Okay, so multiplication is repeated addition. Exponents are repeating multiplication over and over again. So, because an exponent shows repeated multiplication, and we know multiplication makes things grow very quickly, graphing an exponential function like y equals 2 to the x makes it grow very quickly. And vice versa, if you have a negative number out front, it makes it grow down very quickly. Okay, the larger your base, so base 2 versus base of 5, the larger the base, the faster your graph will grow. When we graph, we're going to be trying to work with a table of at least 4 values. 1 negative number, 0, and 2 positive numbers. You can always use more values, but I'm going to expect at least this in your homework, so you might want to jot that down right now. The first thing we want to do is be able to tell if the table represents a linear or exponential function. Remember, a linear graph is our straight line, and we know that they have to grow by the same addition every time. Okay? We always have to grow evenly. And we know exponentials grow by multiplying every time. Okay, so that's going to be our biggest difference. So if you look at your table here, the x's are going +1, and that's good because you have to have consistent x values to tell what happens on the y's. Here you can see it went up by 2, here it went up by 2, and here it went up by 2. The consistent pattern of addition, okay, tells me that this must be a linear function. Okay. Here, if I look, my x values are consistently going up by 1s, so this is good. I can compare my function now. And if I look at my y's, here it looks like I added 2, but here I definitely didn't add 2, so adding can't be the pattern. 2 to 4 works by multiplying by 2, and 4 to 8 works by multiplying by 2, and 8 to 16 works by multiplying by 2. So this pattern is showing repeated multiplication, and that tells me it's an exponential function. Okay? So, which equation is linear and which is exponential? Hopefully, you all recognize this one as linear, being y equals mx plus b. Okay. This one is going to be our exponential function. Because it has an exponent in it, which should be your big clue. Exponential functions are going to fit y equals a times b to the x power. B is called our base. Okay, when we talked about like 2 to the third, 2 was the base. Okay, and x, the exponent, is what we're going to plug into. Remember, you do your base to the power, then you multiply by what's out front. Okay, so this is how our exponential functions are going to look today. The first thing we can do with these exponential functions is evaluate them. an initial population of 20 rabbits. Okay, so initial equals 20. Triples every half year. So it triples in 6 months. The function f of x equals 20 times 3 to the x. Okay, I would encourage you to be writing this down with me. Gives the population after x half-year periods. So this tells us the number of half years, not the number of years. How many rabbits will there be after 2 years or 3 years? Okay, so if we want to know f of 2 years, all right, what number do you have to put in for x? Hopefully, you know that x has to be 4, because in 2 years, there's 4 half years. Okay, so this means 20 times 3 to the 4th. You always do the part with the power first. So 3 to the 4th, or 3 times 3 times 3 times 3, is 81. Because you have a 9 and a 9, and 9 times 9 makes 81. 2 times 81 would be 162, so it's 1,620 rabbits. So f of 2 years, or f of 4, because it's 4 half years, gives me 1,620 rabbits. I would like you to figure out how many rabbits will there be after 3 years. Alright, it's always good to practice your mental math, but if you can't do it in your head, it's good to practice how to do multiplication of large numbers without your calculator, because you're not going to always have it, and yes, I know cell phones, but not going to always have that either. So practice your math. It'll make your brain stronger. Think of it as exercise. So f of 6 equals 14,580 rabbits. And that is how many rabbits there would be after 3 years, because we're talking about half-year periods. Okay, so when you're using an exponential function, plug in for the variable x, make sure you evaluate your exponent first, then take it times whatever else is in your equation. Order of operations. Alright, when we graph exponential functions, I'm going to require you to have at least 4 values in your table. And of those 4 values, I would like to see at least one negative number, at least the number 0, and 2 positives. So, for the sake of repetition, I'm going to use -1, 0, 1, and 2 for this problem. Okay, so now we're going to plug in. And if you learned in grade school about process columns, this is a great time to use them, because it'll help you get all your parts straight as you evaluate. So, I would encourage the process column. So we have a half times 3 to the negative first power. Well, we know negative exponents tell us to move the number down to the denominator. So it's a half times a third, which gives us 1/6. I'm just going to need a little more room in my table, it looks like. Then I'm going to have half times 3 to the 0. Well, we know 3 to the 0 is 1, so this is half times 1, so I get a half. Then I'm going to plug in 1, so half times 3 to the first. Well, that's 3 to the first is just 3, so half times 3 would be 3 over 2, or 1.5. And then my last one, plugging in a 2. Half times 3 squared equals 1/2 times 9. So 9 over 2, or 4.5. Okay. That process column can help you just do your exponents correctly and making sure you're not forgetting anything as you're plugging it in. So -1 for x goes with 1/6 for y. So just try to make it above 0 but not quite at 1 yet. 0 for x gives me half of y, so that has to be slightly higher. 1 gives me 1.5. And 2 gives me 4.5. So you can see how quickly this function grew from really small to shooting up. When you draw it, think of a curve, a swoosh, that never quite touches the x-axis. Okay, so you're going to definitely have arrows on both ends because this graph could go both ways for forever and ever. We would just have to do a lot of calculating. Really, really small over here, really, really big over here. Okay? So exponential functions, swooshes, 4 points, don't touch your x-axis. Let's do one that has a negative number in it. So here I've got the function for you, y equals -1/3 x, 1/3 times 6 to the x. And we're going to make that 3-columned chart again. X, your process, and your y values. So, again, I would choose -1, 0, 1, and 2. If you want to choose 3, we could use 3. Just could get really big. So, -1/3 times 6 to the -1st power equals -1/3 times 1 over 6. Remember, the negative exponent makes it move to the denominator. It doesn't make it a negative number. So this will give me -1/18. Super, super tiny. 0. So -1/3 times 6 to the 0 equals -1/3 times 1, because anything to the 0 power is 1. And I get -1/3. Putting in a 1. -1/3 times 6 to the 1st. Gives me -1/3 times 6, so that is -6 over 3, or -2. And plugging in a 2, -1/3 times 6 to the 2nd equals -1/3 times 36, so that's -36 over 3, or -12. You can see how quickly this went from tiny, tiny fractions to a large number in just 4 units. So -1 is -1/18. I know, it's impossible to make it that small in my graph. 0 is -1/3. 1 plots with -2, and 2 plots to -12. So I actually have to go below my graph. And yes, I want you to graph things even if they go off your paper. You can always label them to tell me where they should be at. And then again, you're going to draw a swoosh, and you want it to keep going, arrows in both directions. And you don't want to touch your x-axis, but you want to like ride right along it. Okay? Exponential function y equals -1/3 x times 6 to the x. It grows really big in a negative way because it started with that negative coefficient. We can do an exponential function with really large values. When you see large numbers in your equation, just remember, don't actually draw your graph out till you have all your points so you know how to calculate your graph paper. Okay, you can zoom out to view a large area on a map. The function f of x equals 100 times 4 to the x models the original area the map shows after zooming out x times. Graph the function. So again, zooming out x times. Can I zoom out a negative number of times? Actually, I can, because that would mean I zoomed in. It'd be the opposite of zooming out. So I am actually going to put in -1, 0, 1, and 2, and use those same values again. So 100 times 4 to the -1st will be 100 times 1/4, or 100 divided by 4 gives me 25. 100 times 4 to the 0 is 100 times 1, or 100. 1. 100 times